Alrighty then. So today we're going to cover the last section of Chapter 6, and then the next couple days after today is going to be a little bit more practice on 6.2, and then some review stuff, and then quest on, I think it's Tuesday of next week. Yeah. Then we move on to Chapter 7. So a little bit more interesting stuff today, real-world situations, talking about laws of growth and decay. You did this last year using, if I say the Pert equation to you, does that make sense? But last year it was like math magic where you were just given this mysterious formula and you plugged and chugged and solved all kinds of problems. We're going to solve those same types of problems now, but we're going to do the calculus and explain where that comes from. Very seldomly will the AP test require you to derive the Pert equation, but you should still know where it comes from. And there's some problems where the Pert equation won't work. And I have the last example that we're going to get to today. Has a situation where the Pert equation doesn't work. It's a little bit of a variation of that aforementioned Pert equation. So to save your hands from falling off, I have 3 examples for you. You can put that iPad away unless you're using it to take notes.
I'm not.
Okay. Unfortunately, a lot of times when we talk about growth and decay, it involves depressing subjects like the spread of disease, zombie invasion, nuclear waste. Not a lot of feel-good going on here. And to be honest, I don't have the energy or the time to try and come up with happy exponential growth and decay problems. What's that?
Like the spread of...
It's okay, I like that. I think we can build off of that. In case you didn't hear Alex, he said the, what'd you say, this?
The amount of people with smiles.
The amount of people with smiles. I think we can work with that, especially given Pert equation, yeah, blah, blah, blah. We're going to talk about the calculus, and then today, be nice to everybody, which might cause the smiles to spread. And it would spread in an exponential growth, right? Because you smile at 2 people, they smile at 2 people.
And Mary scowls at you.
And Mary.
It worked? Awesome. That's 1. 2.
Did you hear what he said?
No, what did he say?
He goes, and Mary like frowns at everyone.
No, I believe it
Wow.
was scowl.
Wow, I'm so sorry.
Scowl even. You went with scowl on that one. Okay. All right, okay. Pert equation. P is the initial amount, E is E, R is the rate of growth or decay. What's the difference between growth and decay as far as R goes? Refresh my memory. Cricket. Okay, so R is the growth rate or the decay rate. How do I tell the difference? And don't tell me one gets bigger and one gets smaller. Numerically. Yes, Greg.
Negative and positive.
Good, which is which?
Decay is negative.
Good. If the R value is negative, we have a decay, which would apply to things like the breakdown of radioactivity, some investments, that kind of stuff. If it's positive, we have a growth, spread of disease, spread of cancer, all these negative things, death rates, that kind of stuff. T is obviously the number of turtles, right? So no, it's time. P naught is the initial amount. P is the ending amount after a certain amount of time. Okay, so you know this already, right? Good, awesome. Now we get into calculus, so we're going to change this a little bit. We're going to start with one of these buggers. This is just the growth, or the Pert equation reworded to suit our needs, where C is your starting amount, K is the growth rate. It's just a different variable to represent the same thing. And then in this case, this is what we're going to use, and actually we'll probably change that C to a K to make things a little bit easier. That C is called the proportionality constant. So the standard is usually to use K for that. Okay? So we're going to go from this to that. And last year, again, you were just given the Pert equation, you plugged and chugged into it, you solved for all the different things, and life was grand. Today we're going to have to talk about how we get that. Okay? So this is probably a problem that you could have thrown into the pre-calc curriculum, and you could have solved it last year. There's nothing fancy about it. But we're going to use calculus to get to that Pert equation. Okay? Because I think the process is important, and like I said, there are some problems that you're not going to be able to use this way. Okay, number of bacteria in a culture increases from 600 to 1,800 in 2 hours, assuming that the rate of increase is directly proportional to the number of bacteria present. Find blah, 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 blah. Okay, first things we need a variable. What variable would you like to use to represent the number of bacteria?
B.
B, good. B equals bacteria. Okay, now we're going to use this sentence here. The rate of increase. How would I represent the rate of increase of the bacteria?
Like R?
Nope. Think calculus.
DBTT.
Good. That's kind of a lot of dBdt. Okay. Because it's a rate. Remember, derivatives represent three things. Slope of the tangent line, rate of change, and instantaneous velocity. That takes care of the first part. Then, is directly proportional to. That's where we get a proportionality constant. You can use whatever variable you want. K is the standard, but sometimes you'll also see alpha used. Okay, so sometimes K or alpha is sometimes used as a proportionality constant. We're going to use K. To the number of bacteria present. Are we good? Gesundheit. That's a standard setup for these types of problems. Occasionally it will vary. In example 3, that'll change and we're not going to be able to just jump to the Pert equation. But that's how we start. Okay, now we're done with the word problem for a while. Now we have to do some calculus, which is a separable differential equation. What's the first thing you must always do in a separable differential equation? I'm sorry? Yeah, separate the differentials. That b belongs over here with the db because the b and the db's go together. The dt goes over here. We're going to leave the k there just because that's the easiest way to do it. 1 over b db is equal to k dt. That's a b. Okay, next step. Integrals. Left side, what's the integral of 1 over b? Yeah, natural log of b. Would have a plus c also, but we'll worry about that in a second. We'll stick it over on the other end. What's the integral of k dt? Kt, correct. Okay? And that's why the differential is so important, because if I just said to you, what's that? Number one, that's sloppy math. And number two, there's two possible answers. Well, there's a lot of different answers. It could be kx, it could be kt, it could be 1/2 k squared if I do this. You with me on that one? So k dt means my variable is t, not k. What's k? It's constant. Good. All right, so pretty much beat a dead horse with that, but we're good to go. And we'll stick the plus c on the t side. We good so far? Good. I don't like the natural log. I'd like to get rid of the natural log. How do I get rid of the natural log? Yeah, do the e raised to trick. Okay, which becomes b. That makes me happy. Now we're going to do a little bit of math. Instead of doing e to the kt plus c, I'm going to break that into two parts. And I'll show you what it breaks into first, and then I'll explain it. Or maybe you could explain it. Do you understand what I just did there? Two people are shaking their head. 7 people are looking at me like I'm speaking Italian.
I know Italian.
Bueno. No, not bueno. I don't know. I don't even know. Pasta primavera? What? Chicken parmesan.
Good job. It's actually Polo di Parmigiano, but
Pizza.
Polio?
Polo.
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 Like the game?
See.
Polio.
But it's 2 L's.
I think I'll pass on the polio primavera. Thank you. This is some good polio. What's x squared times x cubed? X to the 5th. Now do you understand where this came from?
Yeah.
I went backwards. Okay? Now, why did I do that? What's e to the c? What's c plus c? What's c squared? C minus c? E to the c?
C.
Sounds like we're talking
Which sounds like what?
We're all talking Italian now.
C. Or Spanish. Espanol, see?
See.
See. All right, there we go. So all of that just got us to the Pert equation. Now, are you going to do that on every single problem? No. More than likely, let's say we had a quiz tomorrow, I would ask you to derive one equation to show me that you know how to do it. The other problems, you would just go right into the Pert equation. Okay. And obviously with the Pert equation, you have to change some variables. Notice we changed the P to a B. We changed the starting amount to a C. Our rate is now a K instead of an R. Greg has a question?
For that more than likely, did you mean that we just need to know how to be able to do it, or that there'll be a quiz tomorrow?
Stop, it's not funny.
I'm not joking about this.
Oh.
It's not funny.
So you want to know if there's a quiz tomorrow?
Yes.
Yeah, you said more than likely if there were a quiz tomorrow.
Well, there's a couple options we can go with here. I could tell you the truth, or I could lie. Pretty much only two options, right?
Or not even.
Door 3.
Or door number 3, yeah. No, there's no quiz tomorrow.
So you didn't go with door number
Can
3.
you tell
Door
me?
number
I guess option 4 is I could just mess with your heads.
Did you just tell me the truth?
The truth, the whole
Nothing
truth.
but the truth?
There's no quiz tomorrow.
That's more
Can we do door number 3?
All right, there is a quiz tomorrow.
God.
Yes, there's a quiz tomorrow. No, there's no quiz tomorrow. Maybe there's a quiz tomorrow. There's no quiz tomorrow. Okay.
Oh, there we go.
Don't cry, you'll be okay.
That means we have a quiz.
No, don't cry now. You can cry tomorrow during the quiz. Ooh! No, I'm kidding. Seriously, there is no quiz tomorrow. No quiz.
There's actually a quest tomorrow.
I've got a pop test for you. All right, let's get back to the problem. So we start with the Pert equation. If it's a problem where I ask you to derive it, you got to do all that stuff. If I don't, then you go right to this thing. And now we got to solve some problems. Okay. So first of all, we want to know the formula for the bacteria type. For the formula, we need to know what the starting amount is. We need to know what the growth rate is. This is a growth rate, right? Yeah, because it's bacteria, so there's bacteria growing. Okay. I'm going to show you the math to get the starting amount, but practically speaking, if you read carefully, what's the starting amount?
600.
600, okay? Because that's the way the problem is set up. The problem won't always tell you the starting amount, and in fact, mathematically, how do we find the starting amount? Well, I know that at t equals 0, I have 600 bacteria. So I have 600 bacteria when t equals 0. What's e to the 0? 1, so therefore our starting amount is 600. Okay, so that gets us to the next step then. Now we know B is equal to 600 times e to the kt, and now I've got to find k. And if I do my math correctly, k should be a positive value because it's a growth. That's an e. How do I find k? What else do I know from the problem?
It's proportional. 2 hours.
I know it's proportional. What happens after 2 hours?
It gets to 1800.
Good. After 2 hours, my bacteria is 1800. I still started with 600, and I know that I have that. Okay. Beautiful. How do I solve that? Dividing by 600 is a good start.
16.
What is it?
Say again? Beautiful. Take the natural log of both sides. What's the natural log of e to the 2k? 2k. So k is equal to the natural log of 3 divided by 2. 2. Okay. There's my exact value. Now this is where you use your calculator. Go ahead and fire them up. I would like to know a decimal approximation, but we have to be careful here. These calculations get very picky, meaning, well, you tell me. K is approximately what? 0.549. If you continue the problem using 0.549, you're going to be wrong. It's going to be off too much. How do I solve that problem? Store that into somewhere on your calculator. Store it into K, store it into X. Usually I would just use the X button and store it into X. Okay. But for demonstration purposes, I now know that my equation is B is equal to 600 times e to the 0.549 t. 0.5. Mary. There it is, 0.549 t. I knew it would show up eventually. Okay, so that takes care of part A. There's my general formula. My two variables there are my ending amount and my time. And now I can plug and chug all day long. Okay, two questions to answer, or I should say two questions to ask. After T number of hours, how much bacteria do I have? Or I've got a bunch of bacteria, how much time does it take to generate that bacteria? The last one says 4 hours. So we will, let's see, switch to red, put in B equals 600 e to the 0.549 times 4. Nice and easy, plug and chug into your calculator. Make sure you use your stored value. So you would do 600 times e raised to the 4x, if you stored it into x. And it turns out that you have how much bacteria?
5,400.
Say again?
5,400.
5,400. 5,000. Everybody else, we're good? Okay, it's a word problem. 5,400 what? Bacteria, right. Bacteria. Okay? Not so bad, right? Question?
Where's our answer for A? Is it,
A is right here.
okay.
That's the general equation. Okay, so in your general equation, you should have the growth rate or decay rate in there, and you should have the starting amount. And then here's our answer for B. Okay? Good? The tricky part with these problems is getting this initial equation set up, and most of the time it's going to follow the same form. The rate of change of something is proportional to that something. Okay? Good?
Yep.
Can I erase? Next example. Radium. Right? Is that what we're doing? Yeah, radium. This one we're not going to derive. We're going to go right to the Pert equation. And you can use whichever form you want. You can use the C e to the kt. You can use the P naught e to the RT. I don't care. Okay. It's up to you. But we need to talk about half-life. What is half-life other than an awesome video game? Yes, sir.
It's the amount of time it takes something to decay to half its previous amount.
Right. Everybody get that? Because that's an important concept. They won't explain that in a problem. You're expected to know what half-life is. Again, it's the amount of time that it takes for something to decay so that half of it is left. So radiation decays, it just disappears. It breaks down and goes away. And so if I start with 100 milligrams of radium, the half-life is how much time it has for me to get 50 milligrams. Okay? Good. There's also something called a doubling time. Doubling times are commonly used in investments. So when you make an investment, a common question asked is, what's my doubling time? Meaning, how long will it take for my investment to double? Invest $100, how long does it take for me to have $200? Okay, so you don't want an investment that has a half-life. That would be bad. Okay.
Unless you're shorting it.
What's that?
Unless you're shorting it.
Unless you're shorting it.
That's true. Good point. Am I writing here? Yes. Okay, here we go.
You're hedging
Uh,
against it going down.
Let's do, we'll use the radium. So R is equal to CE to the KT. We're just going to go right to that. If I had to derive it, though, I would know that the decay rate, okay, dr dt, would be proportional to the amount of radium I have. So dr over dt would be equal to k times r. But we're going to skip that and go right to this. If I start with 100 milligrams, the half-life will tell me what I have, or what time it'll be, or how long it is after I have 50 milligrams. What if I don't know the starting amount? So notice in the first line of that, I don't know how much I'm starting with. Does it matter? Okay. So for instance, if I start with 100 milligrams, e to the kt, I'm going to end with 50. if I solve this for one of the variable, let's suppose I know the growth rate I'm solving for t, what would I do first? Say again?
Divide by 100.
Divide by 100, and I'd get 1/2. Suppose I start with 1,000,000 tons of radium. The half-life would tell me how long till I have 500,000 tons. It's a lot of radium, by the way. What's the first step? Divide, and what would you get? So therefore, do we need to know the starting amount? No, I know that regardless of what I start with, after a certain amount of time, I'll have half of that quantity. That means I've already eliminated the C and the R, and now I just have e to the kt. But I know what t is. T is 1,600 years. Which is why nuclear accidents are kind of a big deal. It takes a long time for some of this stuff to disappear. Okay, what next? Natural log. So natural log of 1/2 is equal to 1,600 k. So k is equal to the natural log of 1/2 divided by 1,600. Go ahead, tell me what that is. And make sure you store it again, because this is going to be a bizarre number, I think. Oh, by the way, before you type it in, will it be positive or negative?
Negative.
Negative, because it's a decay. What do you got, big boy?
Negative 4.33 to the negative 4.
Yeah. So negative 4 point blah, blah, blah to the negative 4th power. And I don't want to have to retype that in, so I'm just going to ballpark it here. Negative 0.4, you say 433?
Yeah.
433 times 10 to the negative 4th or 3rd, you say? 4th, okay. Fairly small number. It does,
4.3.
Yeah.
negative 4 point, yeah, because it's got to be scientific notation. Come on, Reed, you're better than this. There we go. Too lazy to erase. Okay? So now I know the growth rate. I still don't know how much I started with because it didn't tell me how much I started with until I get into problem A. But now I know the decay rate, so I'm good to go. So part A says find the formula for the amount of time remaining from 50 milligrams of pure radium after T years. Okay? Done. So the amount of radium after, or starting with 50 milligrams would be negative 4.33 times 10 to the negative 4th times T. And you can see why you want to store that number. Okay, so there's the answer to part A. Put a rectangle around that. Part B, when will the amount remaining be 20 milligrams? Where's the 20 go into the equation? R, good. Put it in for R. So not doing a half-life here. We're doing a little bit more than a half-life. First step, divide by 50. So I get 2/5 is equal to e to the negative 4.33 times 10 to the negative 4th t. Natural log. Okay. And when you're done with the problem, after you've typed this into your calculator, ask yourself a simple question. Does that answer make sense? This should be a pretty big number. It takes a while for radium to decay. What do you get for T, by the way?
2,115.
2,115. Somebody confirm?
Yeah.
Okay, 3 decimal places though.
0.85.
And what are those? Years. That's a lot of time. Okay. So the calculus part of this that I did in the first problem, after all that work, would get me down to this point. But in this case, we can go right from that equation and move on. Okay. Questions on any part of that? I'm assuming you're okay with the natural log business there to get those values, right? Okay. Next one doesn't work so well with just going right to a Pert equation. And where would this go? Chem? Anybody in AP Chem? Have you done log cooling stuff?
Not yet.
Do you?
I don't think so.
Oh, all right. You'll see it's not that complicated, so it might not even be in the curriculum, we'll see. Okay, according to Newton's law of cooling, the rate at which the object cools is directly proportional to. Okay, so we need to introduce a variable. What variable do you want to use? We're talking about temperature here. Your initial reaction might be to use T. We probably don't want to use T because we already have time. F
For Fahrenheit.
for Fahrenheit.
K.
Don't want to use K because sometimes you use rate per K.
C for Celsius.
But then we also have the starting amount for C.
And we're using.
How about we just use Y?
Why?
I like F.
Why not?
I like F.
You like F?
Yeah.
All right. dF dt. The rate at which an object cools is directly proportional to the difference in the temperature between the object and the surrounding medium. In other words, the air. Assuming it's in air, it might be in a water bath. Who knows where it's at? That's why it says surrounding medium. So that would be F minus whatever this medium is. The room, the water, whatever it's sitting in. But we know if we read a little bit further, blah, 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 surrounded by air at a temperature of 75 degrees. Okay. So if I stopped at where I was reading at that first sentence, I would introduce another variable there for the temperature of the medium, maybe M. But then as I read the problem a little bit further, I get 75 degrees. Okay. So this one doesn't apply for a Pert equation, because you'll see when we solve this using calculus, we're going to get a little bit of a variation from the standard Pert equation. Separable differential equation, first thing I do is separate the differentials. I'm going to divide by this whole mess. And things will start to look familiar, but it's a little bit different. The right side looks identical, so that'll work out just peachy keen. What about the left side?
One over after 75.
Yeah, and I don't want to just breeze over that. That, from a calculus standpoint, that should be done as a UDU, correct? U would be F minus 75. The derivative of F minus 75 is just 1, so that it works out that way. Because I don't want you to get in the habit of seeing the integral of 1 over anything is just the natural log of that anything. It doesn't always work that way. In this particular case, it would be a UDU, but are you all with me? Do you understand what I'm talking about? Okay, so I won't try not to beat a dead horse there.
Wait, but in the integral, shouldn't it be 1 over F minus 75? It's not.
Oh, you're right. Yeah, sorry. I did my math wrong. I was sloppy.
Okay.
Sorry. Thank you.
That's okay.
There we go. There we go. And then I totally botched that. Because this should be, you guys said it correctly and I wrote it wrong. Natural log of F minus 75. That's what I wanted. And the right side is KT plus C. Okay. Question?
Also, why isn't there absolute values?
Because we're dealing with positive values. Well, I don't know. Could we have a negative value there? Could have negative temperatures. I'm pretty sure we can drop the absolute value, but let me think about it for a little bit and see why we
Because
can
if it's
just.
about cooling, wouldn't the F always be like bigger than the temperature of the surrounding medium?
In this particular case, yes, but I'm in general. I'm thinking more in generalities. Can we just always drop the absolute value? So her explanation is solid for this one, but in general, I'll think about why we can do that. Okay, what do I do next? Because I want to get F by itself, right?
You raise both sides.
Yeah, do the E thing. So this will be F minus 75 equals E to the KT times E to the C. This is an important step. Even though we're going to turn that into a C, you still need to show that you understand how the math works. And so we get F minus 75 is equal to C times e to the kt, which means F is equal to C times e to the kt plus 75. Okay. After all that rigmarole, all it did was stick a plus 75 at the end of that equation. Okay, now we got to find C and we need to find K. How? What do you know about your initial conditions?
Starting at 125 degrees.
Right, so when t equals 0, you're starting at 125 degrees. So this is a $1.25 when t equals 0. So this is 1, and therefore C is 50. So my general equation to start would be F is equal to 50 times e to the kt plus 75. Okay, how do I find K? What other chunk of information do I know?
Next half hour.
Say again?
Find the temperature at next hour.
Not yet. That's our final question. We still have to do our equation, Greg.
F is 100.
When what t is equal to?
30.
1/2, correct. Yeah, we're going to stay in hours here, so you use 0.5 or 1/2 for t. So we would do 100 equals 50 e to the 0.5 t plus 75.
Wait,
0.5K.
You're right. That's easily fixed, thank you. Move the 75 to the other side. Divide by the 50. Natural log of both sides. Blah, blah, blah. Solve for k. Do that, please. And tell me what k is. By the way, will it be positive or negative? Negative. Why k?
Because you're cooling,
So the,
isn't the
Okay.
temperature going down?
alright. What'd you get for a value?
Negative 1.386.
360?
386.
386. Can somebody confirm that?
Yeah.
Beautiful. So F is equal to 50 e to the negative 1.386 t, all of that plus 75. There's our general equation. And again, the general equation is going to have a value put in for C, it's going to have a value put in for K. Then we can use that to answer all kinds of questions. And in fact, the question here is, find the temperature at the end of the next half hour. So after the next half hour, what's T? 1, good, because we're doing a half hour and then another half hour. And a lot of times that last question is the easy part because you did all the hard work early on. Now just plug in 1 for T and solve. Okay, and you know that it's you can use a little bit of logic here and some evaluation skills to know that you should get an answer less than 100, but greater than 75 because it can't cool less than the temperature of the room. Everything strives for equilibrium. Which fits with what we just talked about. It's less than 100, it's greater than 75.
What did you say we should plug in for T?
1.
Why?
Because it's 100 degrees after a half hour, so we've now gone a half hour, and then it says at the end of the next half hour. So we've got 2 half hours.
Oh, I see.
2 times a half is 1.
Yeah.
Senor?
I'm still kind of confused on why at the beginning you used F minus 75.
Because it says in the problem, the rate at which the object cools, that's the dF over dt, is directly proportional to, that's the k, the difference in the temperature between the object, F, and the surrounding medium. And I read a little bit ahead to know that the surrounding medium is 75 degrees. Okay. Can you handle this? Awesome. Okay, and you got a whole variation of problems there. Spread of zombies, disease, all these other fun things. For the most part, you can go right to the Pert equation, but occasionally things like law of cooling, so you have to derive that whole thing. Okay.
This one wasn't that present.
Say what?
This one wasn't present.
No, it wasn't. I mean, but who cares about a coffee cup cooling? I mean, there's
A lot of
not
coffee drinkers.
coffee drinkers. Anybody? Okay, so tea drinker. But yeah, so on the homework tonight, derive 11 and 12. That's it. Every other one you can just Pert equation the crap out of
I'm
it.
so tired.
Okay.
Like,
Okay. So we have some time.